So hello everybody, and welcome to another video. This is the last one for this session of these courses that I've given at AUB for the disciplines. Today we will quickly recap the autoencoder. So this is also a practical that basically was shown in this AUB course for the disciplines. In the last time, basically, we have seen neural networks. We have seen neural networks, how to build basically a classifier for this plant dataset. In this session, we will talk about the autoencoder. It was like the last thing that we've shown, and how you can use the autoencoder in order to build your own data compression algorithm. So what do we need in order to do this? We will this time directly jump into Tensorflow. So we import Tensorflow STF, and we basically import everything that we need again. So we need a couple of layers. We don't need as much as last time. We will make this very straightforward. So just that you get basically an idea about what you can do, basically what kind of different structures you can build, how to interact with the layers of a model, and to see a bit what else you can do than just basically building classifiers and treating images with TensorFlow. So we flatten, we reshape. You already have seen these layers in the last session. Of course, here I need from. Okay, and then we need from TensorFlow. We need again a model in order to build our models here. In this case, the autoencoder. You will see how everything fits together. So let's import all this stuff. We are again in this Colab notebook, as I don't want to install TensorFlow on my machine. You have the right to do so on your own. Either you install TensorFlow on your machine with pip install TensorFlow. This is pretty easy today, or you just run this session in Colab. What happened here? I made a little spelling mistake. Probably, yes, Tensorflow. Model name TensorFlow. We need here models. Okay, so fine, so good. We have everything imported. We start basically here in this session. We will use a very well-known dataset, which is the MNIST dataset. So the MNIST dataset was already used by LeCun, if you remember the previous session, in order to build these neural networks which classified basically images and which allowed to detect basically handwritten digits. So this dataset is a handwritten digit dataset. It is very well known. We will use it here because we are not so interested in the dataset itself, but basically more in these architectural stories that we have. So it comes basically with TensorFlow, so you can directly access it here. Keras datasets and the MNIST dataset, which basically has these little images of digits that we will quickly investigate. So how does this work? This dataset, it comes already with a dataset and with a training and test set. So we will have here labels, of course, and we have basically also a test and a white test set already predefined with this dataset, and we will load this dataset. There's a load data function basically in this dataset, and what we want to do again is, as I told you last time, basically these images, they have like 8 bits per image, 8 bits, so 8 bits per pixel. 8 bits corresponds to a value between 0 and 255, so this is kind of the light intensity at this value, so from black to white. In this case, as these are grayscale images, and we want to have this basically aligned between 0 and 1 for the purpose of this training process here. In general, you can say the way that basically these functions, what are they called right now? These activation functions. The way these activation functions are built, you basically should have always data which is between 0 and 1 on the inputs, and data between 0 and 1 which flows through the neural network. Yeah. Otherwise, you can run into a lot of trouble. So always make sure, think about your activation function. Several activation functions, they cut off below 0. If they explode on the top, it's not nice either, especially if you got something like a sigmoid function or something like this, it will cap at a certain point. Make sure that your data basically on the input is always something between 0 and 1. Then I mean, it's not needed, but you will avoid a lot of trouble. Okay? So far so good. We do this 255, we divide by 255. We do this here again for all these data sets. This is basically, it comes as NumPy arrays, these images, so they're basically nothing else than a NumPy array in a 2D shape, which give you basically the image. Very easy to understand. So just also that you know, we don't need this image loader, the whole data set. In this case, it's just 6,000 images. These images are very small. They are basically, just to recap that, they're basically, I guess 30 by 30 or 32 by 32 pixels big. Just let me get it now. 28 by 28 pixels. They are wide, these images. So they are really small. And 6,000 images of 28 by 28, just with one byte per pixel, fits easily into their memory of today's machines, especially of this coded machine that we have here. Okay, so far so good. So we have our data set here. Let's have a look on what this data set looks like. Let's use the matplotlib basically to just to take one image. So we do this here from matplotlib, import pyplot as plt, and then we basically get here plt. We can then do imshow, so this is perfect for these two-dimensional and NumPy arrays, and we can basically see here that let's take one sample. Let's take the sample number 30 from the tested, so that we can then basically play around by training on the training set, and then we can basically compare what we have on the test set after the data compression. Yeah, so as I said, basically we use this autoencoder. If you remember, the autoencoder is this data structure where you have on one end the large input, on the other end the large output, and in between you have very few nodes. And I told you can use this as a compression algorithm in the lecture. So this is what we will do here. We will use it as a compression algorithm. So far so good. Let's show one image. This is what one image looks like. So these are these handwritten digits. We see that this here is the handwritten number 3. All these images look kind of the same. Let's go here, maybe, I don't know, 120. Just to have some fun. If you see a different digit, this is the digit number 5. So these are basically scans of handwritten images, and this here is just right now from 0 to 1. Basically here, they show the image of this handwritten digit there. And just we basically want to do is we want to train a model where we encode these images, so where we compress this image to a very high compression rate, and then decode these images and hopefully get at least a digit which makes the same sense out of it. Yeah. Okay. So let's go back to our digit number 30. Not to get confused, as I prepared it with this image here. So far so good. It's image number 3. We see this right away. Okay. Of course, in the data set, so as I said, this comes here from the test set. In the training set, you have the same type of images. You can try it out here by replacing X test with X train, and you will see that you will get the same kind of images out. Of course. Okay. So far so good. We want to basically to have here to build our network. So how we will build our network, as I said, we have an encoding phase, a decoding phase. I already have shown you a bit how to build a network in the last time. In this case here, of course, we could do this also with convolutional neural networks. For the sake of simplicity, I just want to show you how an autoencoder works, and I also want to show you basically how you can work a bit with the layers, how you can train a whole network and then look at certain layers, back at certain layers. Let's build a model here. Let's build this encoder model here in a very simple way. So we need an input, of course, no? So we will call this input image here, and it's an input, and basically the shape here. This is a NumPy array of 28 by 28 pixels, so we just call this 28 by 28. This should work basically. We go over here, then we encode, so I will call this the encoded phase, the encoder phase. So encoded. Let's flatten this image right away, so that we have here 28, so that we can basically use this in a linear way. So basically if you imagine each pixel is then connected to these nodes, gives an input to the nodes of the next layer. And we want to work with that straight in that way, and we will call this basically our input image. That's basically it. Yeah. So as you remember, always here the second input to this function here, which defines the layer, basically is the previous layer, and this way you can stack this up, and we will do this in the same fashion as we did it last time. So we will call this here encoded. And then we use directly, as I said, a very simple neural network, so a dense layer with 128 nodes. Activation, a good activation function here is the tangents hyperbolicus, so the hyperbolic tangents here that we will use. And we will basically use here encoded, so just that you also see, I don't know if you have seen this activation function before, but that you can use this activation, that you can use here different activation functions, and that you see more than one at least during this course. So what I will do basically to stack this up here, I will just copy paste this here 2 more times, and we want to encode basically. So let's say, okay, we have here, we go down to 64, and we want to encode basically to 32 values, 32 floating point values basically from this original image. So our original image is 28 by 28. Just let me recap here. So that you see this 28 by 28. We see this is 784 basically bytes that we have encoded. Let's just check. We have then here, we said 32. If these are like even double precision floating points, which they don't need to be, but it's 32 by 8, so we are at 256. We have a ratio. We encode basically from 256 over 784, and we have basically a bit about 1/3 that we encode basically this image in this encoding process. Of course, these floating point numbers, they don't need to be 8-bit, they could be probably 4 bytes. Sorry for that. That's the way basically how this encoding works. So we have 32 floating point numbers. In this case, they're probably double precision. and we want basically which gives us a ratio from the initial data to the data encoded of about 1/3 that we encoded here. We could go probably way further, but let's stay simple. I mean, why do we do this? You can imagine that you can go further because the JPEG images even encode way further. We could use here a convolutional neural network, of course. We could basically do a lot of things in order to make this more advanced. Let's stay with the simple method to see that we can encode the image like this. So this is our encoding phase. Right now we want to go into the decoder phase. So I will call this decoded here. And we go here again then, so we scale up now. So from 32 activation again, we will always use here in this sample this hyperbolic tangent, and we say here encoded as we stack this up on the last basically layer of this encoding stage, and we do this 2 more times to get back to our original image size now. So how do we get there? We basically we scale up. So here we are at 128, and of course we need to get back to the size of our just not make a mistake here, of our image, which was 784, and we don't need encoded here, but we need decoded. No, that's the way it is. So here we need decoded, and this is basically the structure of our autoencoder. Of course we have images on the output, so we want to reshape this into a 2-dimensional shape again. So let's do this here. This is why we have this reshape that we imported, this reshape layer that we have imported at the beginning, and we call this here decoded. And this basically should work right now. The big story is, okay, right now I have my encoder, my decoder. How do I get values from this encoded phase? How do I basically get values from this middle here? How do I get how can I feed values here in order to use this decode phase? And all of this runs around basically about model building. So basically we have one autoencoder that we train, of course, with showing it the input and the output, just as we did it before in the last sample where we built our classifier. But of course that's not everything that we want. No, we want to have a bit more. But let's basically build the complete autoencoder model. So the complete autoencoder model boils down again, as you know, about how to build this model. So the model is basically, it goes from input to decoded, okay, and we want to say autoencoder, let's make it like this, and then of course we want to compile our model, and we will use basically the optimizer. Here is the other delta, and the loss is this binary cross entropy, in order basically, as it's kind of again like a classifier. So if there's an intensity on one pixel, you want to have an intensity on the output pixel. Yeah, this is kind of how it works, and the binary cross entropy should work very well in order to handle this. Okay, so fine, so good. We want to reconstruct the output image from the input image. That's what we want. And this is basically our autoencoder model. Very easy, very simple. This is basically what we have already done in the previous way. Right now we built another model. So basically this is with this model, basically with this one here, we will train it, and we can basically just keep the weights, because we have this model here and we have our layers defined here, and I can say, okay, I want to have another model which I don't really need to compile, but which already exists here. So I do here model, and I say, okay, I take the input image. So let's define this and just stop at the encoded phase. Okay, so basically what this will do, it stops here, and this way, basically by naming this in the right way, I have built my encoder phase. Okay, so if when I train this autoencoder, I adapt the weights on both phases at the same time, and with this one here, I can just basically, with the weights that have been pre-trained, then basically get to the output of this layer. If you name your layers in different ways, of course, with this way you can always inspect what is the value of the nodes at this layer, what is the output basically of, I don't know, of a convolution basically. You can basically do this with this kind of bridge here. Okay, as easy as that. It's a bit more complicated for the decoder. So again, for the encoder, basically for the decoder, we need a new input now, because we want to feed basically our own values to this input. We don't want to go from this encoded phase here. We kind of need a new input and then kind of hijack basically what's happening in between here to push the input in here and take the weights from these 3 layers here in order to get out here. Okay, so fine, so good. Let's do this. Okay, so here I have 4 layers and I want to hack this basically, that I have a new input here and that I get here my output. So how do I do this? So let's build a new input. So I will call this the encoded input. So basically, if I have something that I have encoded prior and then I want to decode it maybe 3 weeks later, as this should be kind of a compression algorithm, we have our encoded input. Okay, encoded input shape. We have here 32 values. We have to write this like this in order to basically keep it, what comes here, to keep this 32 values as an input to this next layer here then. Yeah, okay, so fine, so good. Right now we have to make our trick. We have to define our decoder, and we kind of, what we do here basically is deco, and then we have autoencoder, and as I said, it's going to be a bit strange here, but what we basically do is we count the layers here, and we can basically access the layers from a model that was previously built by that way. So if I would have named this here different, I could just have built the same model for the encoder the way I would build it here for the decoder. But as I have here a new input, I have to build it in this kind of way here, and I want to go back. So this is the -1 layer, the -2 layer, -3 layer, -4 layer. So I go back to the -4th layer, and I say I want to have here the encoded input. And of course I don't train this because I have the weights basically that I've trained by this autoencoder model. Okay, that's the way it works. And as I said, you can stack this up on top of each other, so we can work with this that way. And I can say here layers, and I want to have the -3rd layer, and I have here decoder. Let's do it that way. The -2nd one, decoder, and then I need the -1st one. And I built my autoencoder that way basically. Of course right now I still have to define this model, so the decoder model then of course is the model which goes from the encoded input, so where I can put my numbers basically in that I have gotten out from my encoder stage here, to the decoder. Okay, as easy as that. So you see, very easy. So here my encoder phase, my decoder phase, I can access the layers by that way. This is also very interesting to do, and I can build a model, and basically the weights are always trained by this autoencoder model, and then I have an encoder model which is not trained, which basically uses the weights from this autoencoder model from the encoding phase, and the decoder model which in the same way uses the pre-trained weights from this decoded part here that were trained by the autoencoder. Okay, So fine, so good. I hope I didn't do any spelling mistake, and this whole stuff here should probably basically run. Let's run this cell here in our true Python notebook, and it says here shape is not defined. Probably, yes, I forgot here the equal sign. And we have basically all this here executed. And what happens right now, of course, what we want to do is we want to train, and we need to train pretty hard. So it will take a bit of time. So we have basically here the X-train. And we train, of course, what are our Y labels here? The X-train, no? Because I show the same image to the as I show it to the output. I don't need any labels here. And I want to build, basically, I will use here 150 epochs should be fine for what we're doing, so that we get a little thing of output and the batch size. So how many images do I show it to it simultaneously? Let's make this here maybe 100. And we want to shuffle the images, so we do shuffle through as we read them. And we run our autoencoder, and we basically train our autoencoder. Batch size. This is called here, not batch. And we do this here. And hopefully this is rather fast. This basically runs only on the CPU. The images are so small that the GPU here doesn't have a lot of effect. You see, basically it will take a bit of a while. Let's quickly go over what we're doing while this here trains. Basically we see we have here this input phase here. We have here this output phase here, basically, which we have here. As we went over it, we reshaped this into an image. We have one model, which is the autoencoder, which is currently training. And we have this decoder stage here, which then works as a decoder. Okay, I guess it is faster with the GPU, I'm not sure. It seems to be rather slow, to be honest. But we need 150 epochs. You see that the loss here goes down a bit slowly. I will try to rerun this on the GPU so that you also see basically again. This is pretty fast to do, so we can do change runtime type. We go here to the GPU. We use one T4 GPU. This should be more than enough for this little data set here. And we run this again. So it's connected, and we then actually, in a case like this, you can just do run all, as we run this from the start to the end. At the runtime, we have our moments data set. We see our image, we build our model, and we train already. And we see that indeed this goes a bit faster here. And we see how we get our epochs down here. We already pre-trained a bit, so we should go down basically to something to 0.2, 0.3. Then basically this kind of autoencoder starts to work with this loss function that we have here. Basically this is then finding out, so the more you train, of course, the more accurate it gets. We will just go down here to 0.2, something between 0.2 and 0.3. Of course you can run this at home on a faster machine, on something like this. So I have this running overnight somewhere. In Google Colab this will automatically stop. You probably know this. So after a certain time of inactivity from the browser input, as said, you can run this somewhere else for a very long time and get your autoencoder out here. We train here 150 samples, and we see we're already down to 0.7. We want to go down to something like 0.3, 0.35 should be fine. So we already have done 1/3 of the process, almost. We're at 0.6. This takes a little while. I'm sorry for that. That's the way how it goes. I made it short so that it basically should fit into this video. If you want, you can probably skip forward here. So training is basically finished here. We'll cut the part of this training basically out of this video, don't worry. And what we do here right now is we fitted this. We fitted our autoencoder. Right now we want to use this, so let's see how this works. So right now I can basically do something like this and have my encoding stage that we were talking about. And we can basically use the predict method of this encoder model that we have. And as we said, we trained basically all 3 models simultaneously. So we trained the encoder and the decoder using this autoencoder simultaneously. And let's basically use just this encoder here and say encoder predict. And we take here, for instance, x-test basically 30, and we have to reshape this always to get this into the right way, so that things work correctly. So basically we have here 28 by 28, just to make sure that it's in the right shape. And if I do this here, I have my encoder running. What went wrong here? Encoder predict. This should just work basically like this. So as I said, getting things into the right shape is always a big question. So basically you see the shape basically is like this. So 128, 128 in Tensorflow. So as I said, normally 1 here again, so it's always 4-dimensional kind of the images when they go inside. That's the way it works here. If I type right now my predicted values, so these are my 32 values that we have here, that's basically the whole story about this. And right now what I want basically is I want to use the decoder in order to get my image back, what this looks like if I use these 34 images. So just to remember this test 30 image here, which we encoded. So here this is kind of our encoding stage. So here we compressed it from these 784 bytes to 256 bytes by representing it as these 32 floating point numbers. When we go up here back, we have basically here this number 3, so this is this x-test 30 image that we're using, and we want to see what this looks like when we decode it. So this is our encoded image. Just to know, this is from the test set, so this was not used during the training set, so this way we kind of can test if our autoencoder somehow works. Of course, normally you would do more rigorous tests than this one, but let's basically see what happens. if then I show these predicted images and I can say decoder. Of course I use my decoder phase, which was kind of again trained at the same time as the autoencoder, so encoder and decoder phase were trained at the same time with this autoencoder model, and at the same time we have built this encoder and decoder models. And basically I can use then here the predict, of course, functionality of this model here, and then I have to reshape this here to 28 by 28 after the output so that I can see the image. And we will do this here, and let's watch our image. And this is basically the output image, and we can see that this roughly corresponds to a number 3. Of course, the result is not as satisfactory as one could imagine, so let's just see this. Here's the number 3 that we have here, and we still can see basically that we have a number 3 as an output. Of course, this could be better if you train, of course, your model longer, so you can play around with this here with this training phase. You can increase the number of epochs. If you do 1,000 epochs here, of course you get better reconstructed images out. This is kind of the whole story, everything that I wanted to show you today about this autoencoder, how you can build an autoencoder, how you can use this as a compression algorithm or for all kinds of different things, as I said, also as kind of dimensionality reduction and things like this. I hope you had fun with it. This was kind of the last session. This was also shown at this ALP course. Thank you so much. Have a great day. Bye bye.